Wait, can you hear me still?
Yeah, I can hear you.
Okay. Wait. Am I sharing screen right now? Is that the right screen?
You're sharing your entire screen, yeah.
Okay, that's fine. We need Alvin's Kahoot because I can't start without the Kahoot. Where is Alvin?
Is that the checking code? What do you play the checking code?
This is Alvin's Al, Arc, Ed, Catcher.
Is
So
that
it's,
is that the actual checking code?
I think so. Let me ping cap it again.
No way we made that actual checking code. That's too complicated with brackets everywhere. Wait, what the? Let me go check the checking code. No, that's not the checking code. The checking code is brain.
Wait, really?
Wait, I'll send you the checking code.
Okay, if we change the check code. I thought it was this one.
Do you want me to change the checking code? I don't want. Can we not use a super long one? Like use something simpler than that without the brackets.
Okay, let's just remove the brackets and then the rest of it is.
It's so long.
We were trying to spell architecture with all our names, but I guess it didn't work out. So instead it's gonna be brain.
Okay, I can change it to something else if you want to do something. You can call it arc or something. I don't know.
Okay.
Arc NN. What do you want it to be? Just give me the name.
Architecture. Oh my god.
We rarely use the @ symbol in attendance codes, but
We can't use that symbol?
we usually don't.
Oh.
Okay, the
No,
time.
yeah,
That's
change it.
brackets. Brackets. No, that's fine. It's fine. I just changed it. I should work fine.
We need Alvin's Kahoot. It doesn't work.
Where's Alvin?
I don't know. The rest of it should be fine. Yeah. Oh wait, at architecture.
Yeah, I already changed it.
Okay.
Oh, I think not.
Yeah. Okay, this time I can actually demo the code during the thing.
Wait, are you sure no one's in the waiting room?
Oh.
Okay.
Yeah, there's no one in the waiting room. Oh, there's one person. It's Alvin. Alvin, what's the Kahoot?
Yo, wait, what?
What's the Kahoot? You need to put the link inside the thing.
What are you talking about? A Kahoot is not a link.
What?
Hi, nerds.
Kahoot is checking code. It's a code.
Okay.
I'm ready to kill
Wait,
myself.
Okay, fine. I'll just write it. I'll just call it Kahoot.
Okay, no. So what happens in Kahoot is I share a screen, and the screen will have a code.
Okay. Do you want me to give you share permission or something like that? I'll make you co-host.
Okay. Wait, gotta set the background. Ooh la la. Oh
Yeah.
fuck! I lost all my virtual backgrounds.
Why?
Fucking cool. I have to restart Zoom. I'll BRB.
Where is the Pogger original background? Wait, there's studio effects. What is this? Did this raise my eyebrows? Oh my god. What is this? Okay, no studio background.
Oh, God. I am screaming.
Why?
Because I don't know how to explain the math of the different gates. Should I just, like, not?
Just show the code.
Guys, all my virtual backgrounds disappeared.
Fuck yeah.
Oh no.
Wait, let me try one last thing. BRB.
The code runs, but it's not generating anything. I want to shoot myself. Aya.
Look at this simple yet elegant code. Wait, where is everyone? Why is it just us four? Am I just presenting to Alvin? I'm kind of done.
Wait, what'd you say?
Wait, where is everyone? Am I just presenting to you?
Yeah, I already posted a link. Unless I did something wrong.
Present what to me?
I can present No, you're presenting to me too. I don't know what I'm saying.
Okay.
These people from Liquid Hacks already. Oh shoot! Get on Liquid Hacks.
What is that?
Team Liquid Hackathon.
That's Team Liquid.
Wait, can you join? I can't. I'm already using both of my screens.
Yeah, I'm joining too. One sec.
Do I need to join?
We can just have one person join.
Okay.
Wait, where's everyone? Why is there like no one here? Oh,
Because you have a waiting room.
yeah, but there's no one in the waiting
In
room.
the waiting room. This is
Oh,
bad.
what? Are you serious?
What the fuck?
So s-
Wait, wait. Your link was -3, not -4. Just saying.
Yeah, I changed both -3 and -4 to this one.
Okay.
So,
I'll
so
make-
there shouldn't be any issues.
I'll make Dennis join. Dennis, join.
this is madness.
Yeah, AI and 4 and -3 both do the same thing. And our website's fine. Is this a big donut for today?
What is donut?
0.
No, I think people are gonna come. Like it's just kind of late. Like, see, Dennis can't. Oh, that's Dennis.
Let's go, Dennis.
Oh wait, it's on Twitch, not Zoom.
Oh, so we can all join. Actually, I don't know if it's a good idea.
What is the sound quality?
Please
Alvin.
stop. It's horrid.
Are you starting?
No, I'm just. You want to test it out? Is anyone here?
I'm here.
Here, I'm just gonna join it and test it out myself.
Scuffed.
Scuff. Okay, wait. Does the link work? I'm kind of assessing.
Something's wrong. It's either just bad timing or just no one's here.
Edward's here. Oh shit.
This is a fat rip.
Okay, the link works.
I'm trying to think if it's just after last workshop, people had too many midterms, and also just from the last workshop, it felt too hard. The people aren't coming the second time.
Wait, did not start yet?
Oh, some people.
Where are there people now?
Yeah, some people now.
Wait, it says I can't. It doesn't let me share screen.
Okay, wait. Let me
You can't share screen?
let me stop sharing screen and then you can share screen.
Oh, okay. Oh, it still says host disabled sharing screen.
Okay, you know what? I'm gonna enable it.
Let's go, Ethan.
Ethan.
Okay.
I always see you in
I did it.
ACM, but I don't think we've ever talked. Big
How are
sis.
all y'all's midterms?
Wait, no, stop. Wait, how do you see this?
Oh. Alvin made me do his midterms for him.
Oh shit! What?
I'm not even
Poggers?
kidding.
Dude, no wonder I got such a low score.
Wait, Edward baited me. He said it was at 4:30, but it wasn't.
Wait, it is at 4:30.
Wait, it
4:30 right
is?
now.
Oh wait, what the?
There's no one here. Wait, maybe everyone thinks it's everyone forgot about daylight saving.
Maybe.
True.
I
I thought it was tomorrow.
Big doubt.
Yeah, same thing like when my crush left me on red.
Huh.
Oh, buddy.
Wait, ping everyone again.
Well, I already
Oh, yeah.
did. I already pinged everyone. I'm not gonna ping again.
What if you pinged me instead of everyone?
Oh,
Also,
yeah,
it was
that-
like a super late ping, too.
Okay, let's start. Oh, there's people. Oh no. Oh wait. Okay, let's start.
Wait, get tongue. Edward, tell tongue.
Get tongue. Okay, I'll tag tongue.
We should give out prizes for the cahoots so people come.
So we have
True.
we're very empty on money.
Thanks for volunteering to fund the prizes there.
I'm okay. That's not my job description.
All right, we better be getting some sponsors then from you.
Of course. Well, technically, that's not in my job description either.
Oh, really?
But I mean, I think I still like help out, but like technically, it's not.
Wait, what is your job description?
I don't even know.
Marketing coordinator. But I think it's more like we just work together, basically.
Okay, also, we're going to start in a few minutes. We're just going to let people trickle in before we start with the Kahoot review. And then we move into more
Something
random
smells
neural
good.
networks.
Is someone making something?
What are you making something?
Okay. Checking code is architecture. Yeah, I guess I was actually making some social screen.
That's not the check. Yeah, that's the check code.
Third, 12 people strong. Let's go.
Oh, tongue joint.
Where?
Oh wait, should I play music?
Yeah, play something groovy.
Groovy? I had song thing.
Play the Iron Man. Wait, no, play my playlist. Play my four tongue playlist. Tongue, can you hear this?
What?
Tongue, are you here?
No,
Wait,
No.
wait, Edward, play my four tongue playlist.
that's so cute, Alvin.
What?
No, go on Spotify and play four tongue.
For tongue?
Yeah,
What is for tongue?
you'll see it.
Where is tongue?
No, Alvin, no, go to Alvin. No, that's not, what are you doing? No, my name is Alvin.
Did you actually make your name Alvin?
No, that's not me. That's not me.
Scuff, I can't find you.
No, Alvin Wing 922.
Alvin Wayne 922.
That's me.
Wait, you don't have to do it. You don't have to do it. It's okay. So weird.
Can you hear it? I don't think so.
You know, go into the playlist. There's a fire.
Hello,
Hey, Alvin.
I'm not where I'm supposed to be. I hope that you're missing me.
Okay,
Makes me
let's start
feel
at,
young.
That's so loud.
Hello. That time that I saw your face was recent in second grade.
What?
It's too loud.
Wait, but it's like super quiet for me.
We should have had that as part of the recording. Oh, someone's recording.
Wait,
Is Dennis
are you recording?
presenting?
Yeah, Dennis.
Okay, Kevin. Let's go.
Okay.
Do you want to get more ping again?
Wait, what close should it be? Okay, let's start at 440.
Okay.
I'm gonna get water.
Sure, you should do one more ping.
What?
You should do one more ping.
Okay, fine, if you insist. Announcements?
Oh,
Okay.
you want to talk about the competition, the neural network one?
Oh wait, we can.
Or do you want to talk about it next week?
Well, yeah, we should say that we're introducing that.
We should probably talk about it now in case some people miss it next week or the week after.
Oh, we haven't finished the slides for those yet.
I mean, you can just mention what the competition is. It's basically, yeah. Okay, I'll talk about it briefly. If you guys don't know, after the competition ends tomorrow, we'll have another one starting in 2 weeks. It basically the only knowledge you need is like our first workshop, and then we're gonna teach you guys all how to code for it.
You're echoing a lot.
Do I have like a voice lag or something?
At least
Wait.
for me, it's like really echoey.
Is it still echoey?
Okay, I think it's better now.
Oh, okay. So in maybe not 2 weeks, I think 1.5 weeks, we're gonna be running a workshop on Keras, on how to use Keras to like write neural networks really easily. In addition to that, we're gonna be introducing everyone to our new neural network competition. Basically, it's just you can use whatever concepts you learned from the past workshops, and you'll create your own neural network to try to model some function we give you. And whoever models the function best wins. We're gonna have an online leaderboard on the website, similar to the one we have right now. So we'll post everyone's test scores not test. I don't want to call it test score. Everyone's accuracy scores online. If whoever ranks has the highest accuracy or lowest loss, whichever metric we use, will be ranked first, and we'll give you an honorable mention in our Discord.
Oh, shit. Okay. Should we still wait or should we just start?
Oh wait, I forgot to advertise this twice.
Yeah, you should advertise this first.
We should just get started after that.
Yeah, let's get started. Actually, no, it's okay. I don't know if they'll join.
Who else should I tag? Okay. Should we wait, Alvin, are you sharing screen for the Kahoot?
Yeah, probably.
Okay. I'll stop sharing screen right after. Oh.
Oh, you gotta make sure. Is someone watching the what's it called? The waiting room?
I'm looking at it. I'm looking at it. Don't worry.
Okay.
Just
I
start
guess
like and let people just start going on it.
Okay. So this is our workshop. Today's workshop is going to be on neural network architecture selection. And this is going to be the 4th workshop in our neural network series. So to start off with, we're going to do a Kahoot. And Alvin, can you share screen for the Kahoot?
Yeah, I got you. Do you want to record? Oh, you're already recording. Okay.
Yeah.
Let me just start it up. Give me one sec. Winner gets free clock. Oh my god. Guys, look, Trista's done.
I know.
He just picked me.
All right. 1, 2, 3, 4. Oh wait, hold on. Number next. Anyone else? How you doing? Or should we start? Edward, do you want to start or do you want to wait? 7.
I guess we could just start then.
Oh, back to me. All right, I'm starting. Last call. 3, 2, 1.
Oh god.
Who still has more midterms? That's so sad.
I have one on Monday.
Oof.
Here I am.
Zipper.
Edward.
2 Edwards. Nickname. Miles Brown. nickname is on a streak. Not something we want to avoid. Ooh, still on a streak, nickname. They're all correct. They're all ways to fix overfitting. It is stochastic gradient. No one put Edward. So sad. Who's in first place? Whose nickname? %. Correct. There's anagram. Damn, whose nickname? All right, last question. All right, let's see who's in first place. Probably Zipper in third. Who's Zipper? You guys want cloud? You guys can drop your.
Yeah, I want cloud. Give me cloud.
What?
Give me cloud.
Which one were you?
Nickname, boy.
Damn. 10 out of 10, dude. That's insane.
Thank you.
Augers.
Wait, do top 3 get cloud? Or just
Top
first
3
place?
get cloud, yes.
Yo, I'm
gets it.
Zipper.
Which one is Zipper?
Number
I'm
3.
Zipper.
Mr. Zipper. Okay.
Yeah.
And who's second? Who's Miles Morales? No? No one else is named that not? Alright, I'm gonna stop sharing.
1% off.
Okay, so just a recap of what we did last time. We went over, like last workshop was about optimization. We talked about neural network regularization techniques, bias and weight initialization, how to fix overfitting, optimizers. And so I guess the question now is, we've talked about how to optimize our loss functions, but now how do we like optimize the layers themselves? So the agenda for today is that we're going to talk about the purpose of having different layers, like specific layers for specific problems, types of different layers, and types of neural networks, and how the specific layers inside these neural networks are different. And then we're going to have some like code implementation sprinkled in between these, and also a live demo of learning afterwards. So to just like get started off with, I think the most the most well-known problem in AI is just the idea of computer vision and image classification specifically. So this is a convolutional neural network, which is the most fundamental way of classifying images. So it gives an input image and then it applies multiple different layers like convolution, pooling, and then it goes to some fully connected layers, and then the output is a probability of what that picture represents. And so for this workshop, we're going to talk about all of these types of different layers and how they interact with each other. So I guess the question now is just why different layers? In our previous workshop, we talked about only using fully connected layers, which are layers that are like just fully connected, where all the weights in one layer are connected to the weights and biases of the prior layer and the layers after that. However, some tasks can't be accomplished with just a fully connected layer, such as feature extraction or remembering prior inputs. And as a result, we will need special layers. However, we should notice that layers are still trained in the same manner as a standard neural network. So the first layer we're going to talk about is the dense fully connected layer, which is also known as the feed-forward layer or linear layer, depending on what algorithm or what papers you're reading. All neurons in the layer are connected to all neurons in the previous layer and also all neurons in the prior layer. And the most commonly used layer, and it's also the most commonly used layer. Yeah, so the layers that we used from all the previous workshops are all dense layers. And the dimensionality of dense fully connected layers are comma n dimensional, where n is the number of neurons in the layer. Notice this comma here, which represents that there can be something before it, which is going to be the batch or how many different things are fed into the network at once. And so this is just like a picture of the dense layer itself. And the next thing is called a dropout layer. So what a dropout layer is that sometimes during our training, there might be instances where one layer or some specific weights are just like really large, and this causes overfitting, which is kind of the problem we were trying to address in last week's workshop about optimization. So this is just like a specific layer that kind of solves this issue by optimizing the neural network in place. So how this works is that it specifies a probability in which each neuron in the layer will be dropped. And in other words, it just zeroes out the weights if chosen as a dropout neuron. And this causes specific weights to have more effect on the final output as the other ones are just initialized to 0. And what this essentially solves is the problem of overfitting, which is when the model learns noise in the training set due to training set being too small, and it also reduces performance on unseen data sets. And so how this works is that it just introduces noise into the network itself, which is a good thing. And the dimensionality of this can vary, but it's usually done right after dense neural networks. So the dimensionality will be the same as the dense neural network. And now Alvin will talk about max pooling layers.
Yeah. So wait, am I echoing? Who's causing the echo? Is it just me or am I echoing? You are.
Yeah, you're echoing.
Oh, no, wait. Test. What the heck? Am I still echoing? Oh my god. I don't know how to fix it.
Hello? Is this better? Okay, perfect. Okay, so sometimes when we're looking at pictures, you have like each picture is made up of so many pixels, right? And if you're trying to put these pictures inside a neural network, it could take a really long time to look through every single pixel. So sometimes we use pooling layers to make this process a little faster. And today we're going to talk about two of these pooling layers, max pooling layer and average pooling layer. So in max pooling layer, we want to reduce the parameters to learn, right? So what we do is we take an n times m rectangle, and in each of these rectangles, we output the max value of those pixels. And there's this term called stride, which is how many pixels we slide across for each of these n times m rectangles. And don't worry, we'll show an example right after this. But what this basically does is it helps achieve translation invariance, because translating the image in this case would not affect the output. And it's very useful when you're trying to extract defining features out of an image, because you're just taking like each square and you're taking like the most defining pixel in that square, thus max pooling. And this also retains the dimensionality of the 3D array, but it does reduce the number of values in the array. So we're going to look at an example of max pooling. Edward. So we're going to look at like a 2 times 2 max pooling layer with a stride of 2. So what this means is we're going to be looking at each 2 by 2 square of pixels, and each stride is 2. We're striding by 2 pixels. And so if you want to go to the next slide, Edward, we're going to start with this first square. It's a 2 by 2 square, and we take the max pixel value in this square, which is 130. And then next we move by a stride of 2. So we move over 2 pixels, and now we're looking at this next 2 by 2 square. And the max number in this 2 by 2 square is 99. And then if you want to keep going, Edward, and then 109, and then 54. So out of this output, out of this 4 by 4 square, we are now down to a 2 by 2 square, which is less data to throw into our neural network. But we still take all the defining features of our image. And so, okay, and another pooling method is average pooling, which I mentioned earlier. And this is very similar to max pooling, but rather than taking the max value at each of those squares, we're taking the average value. This kind of smooths out our input because rather than taking just like that most defining features, we're taking like an average of all those pixels in that square. And this helps retain the dimensionality of 3 arrays, but it reduces the number of values in the array as well. So in global max pooling, the pool size is, wait, what? Outputs 1 value. Okay, yeah. So in both of these methods, we're outputting 1 value for like the whole input. So now we're going to take a look at an example of the average pooling layer. So this is an average pooling layer. So rather than show like every single step, because it's very similar to a max pooling layer, we're just going to show you the final product, which is basically each of these squares is an average of each 2 by 2 square, because we're still doing a 2 by 2 max pooling with a stride of 2. And if you guys have any questions, feel free to drop it in chat. So here we have a question. So which dropout layer do we want to use if we want to the following action, which is you're taking this entire 4 by 4 pixels square, and you are putting it down into just a 1 pixel of 130. Do you have a poll for this, Edward, or no?
No.
Oof. All right. Well, we have A, B, C, D, and E. If people want to drop their answers in chat, that'd be great. We have Kevin Nguyen saying go Wobble Max. I'm assuming he's referring to A, Global Max. Any other answers? A, we have a lot of A. Let's go for 1 or 2 more answers if anyone else wants to answer. All right, if not, that's okay. We can just reveal the answer. So it is actually global max pooling, and it is because you're taking the maximum pixel value in this entire square, which is 130. So sometimes when we are using pooling layers, we encounter errors. There's some pixel values that won't be considered as much as other pixel values because they're in the corners. So when you're, let's say you're each time you're shifting number of pixels is not equal to the size. So sometimes you'll consider certain pixels more than other pixels. And so one way we can fix this is with padding. Next slide, Edward. So what we do in padding is we go around the entire the image, and we add pixel values of 0 around the entire image. And what this helps us do is by adding these layers of numbers, which is we usually use 0, it allows for more accurate analysis of images because the impact of each pixel is now more equal. And another thing that this fixes is that the dimensions before and after you do pooling layers, it will be equal. Because another thing you may have noticed is when, for example, when we did the 2 by 2 max pooling, we are taking each 2 by 2 pixel square, and we're only outputting 1 pixel. And so as you'll notice, the dimensions of these are now mismatched, right? This is a 4 by 4 square, and this is a 2 by 2 square. So by using padding, we can ensure that the sizes stay the same. And then how do we take like our data, like after we do like pooling layers or whatever, how do we take these images and put it in the neural network? So to do that, we use this thing called flattening. Edward, next slide. So flattening is basically, it's in the name. We flatten this pooled feature map into a single column. And if you think about like a neural network, you have like a line of neurons and stuff like that. And so what these dense layers, they only take 1D input, and other layers output a 3D input. So we need to flatten this 3D input into 1D. And so you can kind of see an example image on the left. And we also have some code to show this off, Edward, if you want to pull out the code. So this is some code that, oh, I forgot to mention that we also have code for max pooling and average pooling. So after we initialize our convolutional layers, we have conv11 and conv12. We then run, we have max1, which is like a max pool, average1, which is like an average pooling. Oh, well, Edward, do you want to explain this?
Okay, so for this is just like a lot of sample code where you can sample each of the different types of layers. We were going to talk about convolutional layers and these other layers later on. But for now, we can just sample how these layers work. So basically, essentially, in previous workshops, we used the sequential model introduced in Keras, which is where you essentially just add layers. But this time I'm using a different type of way to create a model, which is just creating it by defining inputs and also the output, while also linking the layers together by just adding the image input at the start. So to demonstrate max pooling, all you would have to do is just take the input layer, which is this line, and then get this max layer, which is this line. So it's like a filter, 2x2 filter with a stride of 2.2. And then this is going to be the output of this. And all we have to do is just compile it, and then it'll just predict. So what this predict is doing is that this is just going to show the output of what one max pooling layer would do. So we can just like try running that. So yeah, at the top of here, it just shows what's going on. So the input size is a 64 by 64 by 3 output shape. This output shape is really standard in pictures because 64 by 64 is its height and width, and 3 is the RGB depth. So what happens with this max pooling layer is that it converts the 64 by 64 by 3 input into a 32 by 32 by 3 output. And notice that this is none. This is just like the batch. Because we only have one picture, then the batch is going to be none because it's just one thing. And then we can see that in the shape of the input and also the shape of the output. So this is just like the NumPy printout of this whole input, and this is the NumPy printout of the whole output. And what we can kind of see, which is like really cool, is that since we know that this is actually the RGB values, or like the randomized initialized RGB values. So in order to get the max pool, the max 2x2 pool, we would do this pixel, this one, and there's going to be some after that, and then you'd pool that by this one and this one. So then we just take the max of this value, this value, this value, and this value, and you see that the max of those three is going to be the 0.98. And then when you scroll down to the bottom here, we can also see that the max pool of that value is also 0.98. So that's just like a demonstration of max. So then we can also do the same thing for average. So we can just do something like this. Image input. So this does is that it makes it so that the image input is connected to the average layer. And then all we have to do is make this the output layer. This can be extrapolated to just like really large networks because all we have to do is just continue linking these together and it'll just become a really large network. But for now, I can just show the average layer, and also, I guess just for fun purposes, we can show this one along with the global max layer, and then just output the global max. So what we expect the global max to do is that this layer average is going to give a 32 by 32 by 3 feature map. Python. It's going to give a 32 by 32 by 3 feature map, and then the global max is going to just compress this into it's going to compress it into a 32 by 32 by, no, it's not. It's going to become like a 3 value. So we can just test that out. Okay, I don't know. Yeah, see, it's gonna become a 3 value. Yeah. Thank you for your input. Yeah, so it's gonna become a 3 value. And the reasoning is because it just compressed this 32 average pool into 1 value and also the 32 into 1 value also. And this just becomes, I think this is at the bottom. Yeah, it just becomes these 3 values, which are the average of the values themselves. And then we can get like kind of a similar result using, if we just put the output into a flatten layer, which will flatten the 32 by 32 by 3 value into a 32 times 32 times 3 value. And we can see that by doing this. Yeah, so you can see that this is just these 3 values multiplied together and you get this value. That's like pretty cool. And then the last is just to use the dropout and the flatten layers. So what we can just do is just use sense1. You just put this in. And you can like change the values of this, but this is just like a demonstration of what Keras is good at doing. So we can see that this is like the whole network and how it's like connected. So it's like input 1 is connected to the block average pool, then it's connected to the flatten layer, then the dropout, then the dense layer. So yeah, that's basically how this code works. And then we can just kind of see the results in the NumPy arrays. Okay. So that's like a really good segue into convolutional neural networks themselves. So a convolutional neural network is just like a network with convolutional layers. And most of the neural network will be focused on extracting features, defining features of the image themselves. So let's say like the curvature of like some foot or something like that. And then the last couple of layers is going to be used for the classification task or any other tasks you have. And this is commonly used in computer vision applications. And so this is like kind of like a shape of what's going on. So you can have like a massive like base or a massive model just for convolution. And you're going to attach like a couple of layers at the end just for classification. So the fundamental kind of layer that's used in CNNs is the convolutional layer. This is specifically the convolution 2D layer because this is taking a 2D input. There's also convolution 1D and also convolution 3D, but those aren't as used as much as the convolutional 2D network. So what the convolutional 2D network does is that it first extracts many distinguishing features from images, and then it multiplies the pixels of each section of the image by an n by n matrix kernel. Like as you can see here, it's like this yellow blot. And then it takes the sum of each entry in the matrix multiplication and sets that value to the corresponding pixel location in the new image. So as you can see, like it's just multiplying each of them and then putting it there. And this takes place at each neuron in the convolutional layer with a unique kernel. And then the kernel and biases are both trained in the convolutional layers. So as you can see, this is like kind of what's going to happen. So we initially have this shoe, and then after applying convolution to it, it's going to look like something like this. And then what we can see is that it kind of like emphasizes this whole like curvature of this top of the shoe. So how is this like kind of relevant? Many existing architectures already use some combination of convolutional and max pooling layers like BGG16, Resnet 18, and a lot of different architectures. So I guess the takeaway from that is that we don't need to necessarily make our own feature extractors, and we can just use pre-existing feature extractors and just retrain our own classification layers on them. However, the whole idea behind all of them is that we want to use a combination of max pooling and also convolutional layers such that we can reduce the input size, which is going to be the size of the image, which is 128 by 3, into some feature set, which is going to be something like this, where 3 by 3 is the size of the feature and 512 is the number of features. So this is like an example of an architecture, and this case is BGG16. So this is just the classification part, and this is the feature extraction part, and this is the classification part. And so I guess the main takeaway is that there are like a lot of really different layers that are like specially created for specific purposes. One such layer is the ROI pooling layer. So what ROI pooling layer allows you to do is that you can do image segmentation and classification at the same time. So in this previous layer, all we do is that we can only classify the image, like this whole image, including the background and all of the other random stuff in the image. However, by doing image segmentation and also classification, we will be able to just extract what we want in the image themselves. So in order to do that, we would first have a region proposal network, which essentially outputs the proposed regions where the target is. So let's say we think the image is in like this kind of square. And so what happens is that the region, it'll just propose this as the region, and then it'll map this. So the ROI will just map this into this kind of square. This is going to be based on the features that were extracted using the convolutional base. So the region proposal network just is just mapped onto the features themselves. However, typically the proposed regions are different sizes, and when they're mapped onto the features, they'll take much longer to process and classify later on. However, using the region of interest pooling layer or ROI pooling layer, it standardizes the size of the proposed regions on a feature map to some predetermined value. Like this is like some 5x7 square, or yeah, 5x7 square, and it'll just standardize this into a 2x2, which is going to be much faster to train. And the ROI pooling layer is basically using max pooling since it takes the max of these inputs. So the really unique thing about ROI is that it doesn't need to take necessarily the halfway point. As you can see, these squares are all different sizes because it isn't able to just cut perfectly in half. So I guess the question is, how do convolutional layers differ from pooling layers? And these are the options. So you can just like put them in the chat. Okay, someone put B. Does anyone else have any other guesses? C. So I guess I'll just wait for like one more answer, and then I'll just stop it. Okay. So it turns out the answer isn't actually C. It's actually E. The reasoning for this is because the kernel isn't predefined by the kernel doesn't necessarily have to be different in the sense that, as you can see here, the kernel is a 3x3 matrix, but you can easily also make it a 2x2 matrix or something like that. So the kernel necessarily doesn't have to be different. And the convolutional layer reduces the size of the input, but so does the max pooling layer, as we can see here, because it's just taking this like really large square and turning it into a much smaller square. And the same goes for A, which is they take different dimensional input. Yeah, so all of them take like a three-dimensional array. So that is false also. So the answer was E. And then now we're going to talk about recurrent neural networks and specifically how they're unique in the sense that they have like cool layers in them.
Hello. Hi. So I'm going to be talking about recurrent neural networks. So we talked a lot about CNNs, but that's mainly for image recognition since it has special, like kernels that can find cool features as it slides over an image. But recurrent neural networks are for something really different. So if you look at the structure itself, it's kind of, all of its neurons are kind of attached to its previous like neurons. So it kind of has some sense of like history, which makes it really great for kind of like text generation or like predicting what is your next, what word is going to come next if you were to pass in like a sentence. So even though this is kind of different, it also still uses a dense layer at the very end, and you can also use dropout. Also, there's It also uses backpropagation since you can still calculate loss and all of those things, but it's kind of different because you have a different structure, so you kind of require a different backpropagation technique. Next slide. So what RNNs and just LSTMs use is something called backpropagation through time. Previously, backpropagation was something we used to update the weights and find the gradients in multi-layer or CNNs. But in backpropagation through time, since RNNs are sequential, they're kind of more connected, so they require a special update. Though essentially it's the same as backpropagation on a normal network if you just like expand everything. So next slide. So in the forward pass, we kind of we calculate our input y at each time step via while also taking into account like what the previous like hidden value was. So this isn't, oh, it wasn't indicated here, but we'll still calculate, we'll still have an activation at each time step and then get our y value, but then we'll also include our like previous like time step value and use a matrix multiplication there. And then we'll continue to do this. So it like kind of builds, as you can see. Yeah, and then like these inputs could be like words, they could be, you know, characters, really depends on what you're trying to predict. So, and also, yeah, you can also have random initialization, like you can initialize to 0, or you can have a special initialization method. So next slide. And then you also calculate the loss in the same way. So at each time step, you would still try to find, like, for example, if you had something that was trying to predict text, you would still calculate the loss by seeing, oh, what is the actual word at this time step versus what my model predicted at this time step. So that's slightly different, but it still works in the same way. Next slide. So then after you calculate the loss, oh, wait. Oh yeah, yeah, after you calculate the loss, you of course have to like backpropagate. And since RNNs have a special method called backpropagation through time, you want to first find the gradient at your current time step, but that will also include the gradient at your previous time step. And then that, like, so if I were trying to find the gradient at h sub 4, I would also need to include the gradient at h sub 3 in my calculation, though I did not include this in the picture, but that is because since our current time step is also tied to previous time steps, we would need to include those previous gradients. So go to the next step. This would also cause a huge problem, like mathematically, because if we were to find like the gradient of like all of our time steps, include that in our current time step, if there is some gradient that's a very, you know, small value, our gradient is going to if it's either a very small value or a very large value, our gradients can explode really fast, or vanish if it's a very low value. Also, this is very computationally expensive because we need a lot of gradients for each step, so we need to keep track, and that takes up a lot of memory. Lastly, it just doesn't scale because of that. And also another reason, like just a more applied reason, is that, you know, if you were in the middle of like a paragraph, like why would you wouldn't want your current value to be as attached to like maybe a word from like the last paragraph, because, you know, they're probably not very connected. So yeah, we kind of need a solution to this. So next slide. And LSTMs are kind of also a sequential model that fixes this issue. So instead of having, so we had an activation in our RNN, and that's usually TANH, and it's just TANH. But what we have here is like the special cell where you do more than just like a simple activation. You kind of have multiple. And there's a reason for each one. It contains like 3 different gates. So first, we considered like the first gate, the sigmoid attached to the X, and then the second gate, the TANH attached to the sigmoid, and then the last gate to be, oh, that's also TANH attached to a sigmoid. But basically, those are the 3 gates that are involved in like this special cell. And the most important part is like the first gate that we're going to see. Go to the next step. And that's called a forget gate. So that's kind of what LSTMs are known for. So you take in your hidden value from, or basically your function value from your previous time step, and then you input your input or X at that time step, at your current time step. And then you pass it into a sigmoid. So just a reminder, the sigmoid outputs a value between 0 and 1. And what you want to do is to have this kind of decide like what value you want to forget. So for instance, you know, if you had a word that came like from a very long time ago, you would want that to have less influence, and you would want to forget that word, for example. So the next 2 gates are more for like updating based on what you forget. And yeah, next slide. There's also a lot more that we haven't covered. So yeah, you can see like there's RNNs here and LSTMs, and then feed forward and perceptrons that we've covered in previous workshops. But there's also another optimization to specifically for sequential models called the gated recurrent unit. I don't know much about that, but we might cover that in the future. And then there's autoencoders and variational autoencoders, which I have used before for like generating like new drawings. And then, yeah. So there's a lot to learn more about. Any questions before we move on to the coding portion or showing some of the code? All right. So yeah, okay. Can I share screen right now? Give me 1 second. Oh, sorry, as I shared my screen, the thing froze. Here we go. Yeah, so it's actually still running for me, but basically, okay, it says RNN, but this is an LSTM, especially if you're working with text data, which I am. I just downloaded like 1984 from like Project Gutenberg. So what's happening here is that first I have to like do a 1-hot encoding. So I'm just finding all of like the unique words in here and then putting that in my dictionary so that I can make a vectorized version of it. So yeah, I was running this before, and honestly, it still hasn't finished, which is why there's so much console output. But then the next thing you want to do is you want to create like what each time step or batch consists of. So, okay, it's kind of like confusing in RNNs, and I'm honestly still don't understand this that much, but basically to predict the next time step, you can choose like how many previous time steps you want to use. And so you kind of have to structure it in that way, or else you'll get like a resize error. So that's kind of what I'm doing. And then we can pass that into the model. This is just another way. I know Edward used the like layers is equal to, and that kind of like acts in the same way as this. Yeah, so then I have like one LSTM layer with 128 neurons, and then I input like all of my text, all of my vectorized text. And then at the end, it's like pretty similar to CNNs where you need like some sort of dense layer for feed forward purposes. Yeah, so then, okay, I'll just go to my output. Let's see. Yeah, so you kind of have to initialize each of the, or sorry, you initialize each of the, like to start the generation, you kind of have to like input some words previously. So this is kind of what's going on. And then, yeah, this happened at each epoch, and then it evaluates its loss. And yeah, then it generates text. And then if you wanted to do an RNN, it's in Keras. You also have simple RNN, so it's just a pretty simple like switch, right? Wait, sorry. Like right here, you can do like instead of LSTM, you can do simple RNN or like gated recurrent units. It's pretty nice. Let's see where I am right now. Yeah, I have yeah. So if I had more time, I would have improved it by removing like some of the punctuation and also like some of the spacing to make it cleaner. Anyways. So yeah. That's pretty much our workshop. Does anyone have any questions? Edward, Alvin, do you have anything you want to add?
You can look at so we have some resources that you can look at later on. This one is a really good explanation of backpropagation through time, the recurrent neural networks, and also about dropout and essentially how it works. And then our code can be found here. So if you click on it, you can just see the code. Yeah. Okay, yeah.
How do I get my cloud again from the Kahoot in the beginning?
Edward, can you please handle that? Thanks.
Wait, Catherine, can you handle that?
What, getting cloud? We'll include you in our announcements after we post the recording.
Okay, thank
So
you.
then everyone knows.
Wait, what's your Discord?
Yeah, what's your
Zipper, ZIPPER, ZIPPER.
Oh, you're that dude. Okay.
Yeah, I'm that dude.
What does that mean, Stone? What is that supposed to mean?
Yeah.
He's posting bugs in a bugs channel. I was fixing them.
You're welcome.
Thank you. Do you have a better strategy now, or are you still third?
I'm gonna work on it today. I mean, I'm just a freshman, so.
Well, not gonna lie, do you know the guy in first place is a high school student?
Oh no, I did not know that.
So...
Okay, yeah, all right. I see how it is.
No, but he's a really smart high school dude. I've known him from another competition that does something similar. So he's done this more than once.
Yeah, this is my first like bot AI sort of thing, but
yeah, this is
pretty fun.
Uncommon. But the next competition you might have a better chance because that's a bit more pure AI, and if you've done these workshops, you kind of know what to do.
Well, I don't know. I don't really, I don't have much experience with the code implementation of the AI stuff. So
we're gonna have a workshop on it in a week and a half. So purely just about Keras and how to make your own neural network and how to chain things together. So Edward showed you earlier how we create a network with average pooling, max pooling, whatever, goal pooling, and convolutional layers. So the way you kind of stack those layers together, there's a really nice way of doing Keras. We'll show you how you to do that in a week and a half.
All right. Sounds good.
Wait, Alvin, what do you mean savage? I just stated a fact.
You try to just roasting him.
Not really a roast. Actually, I don't think Zipper's in second. Whoever's in second is another person. I don't know who it is. Is that Kevin? I've never heard this guy named Kevin, but I don't know who it is.
Would anyone like to unmute, unpin me?
Poggers.
Oh, okay. Oh, it's not that Kevin then. There's a Kevin Z, but he's not in this workshop, so I don't know who it is.
Who wants a sneak peek of the competition?
The graph. If you show the graph, no one can get the answer anyway. Just show the graph.
Oh wait, that is true. Okay.
Like it's probably fine. There's no way you can guess what the function is.
Okay, I'm just gonna not show the function itself, and then
If you show the functions over,
I didn't show the function. Where did I put this file?
I can just send a picture.
But I don't have a picture of the thing.
No, you sent it to the workshop.
Oh, I don't know where it is. I think it's here.
Oh, okay.
I can't find my file. Oh, I'm pretty sure. Oh, it's here. Oh, that's so.
How do you use
Oh wait, no, it's training. Okay, this is a really crappy implementation, but it gets the job done.
Wait, a loss of 42?
It starts dropping later on, like really fast. I don't know why it suddenly drops like really fast. It gradually drops.
Might be because of the
Stop recording.
don't you use like, I don't want to say it out